Kiddos, let's wrap up this chapter with a little problem. We are going to, let me erase some of this so it's not quite so claustrophobic here. We are going to find out how much heat is required for a change in a substance. Looks like it's going to be ice, 25 grams of ice at negative 55, all the way to steam at 225 degrees Celsius. So we're going to have to go through a couple of phase changes here, which means we're going to be using heat of fusion and heat of vaporization. So let me walk you through this to help you calculate or find the total amount of energy required, in this case required, to make this change, because we're going from a low temperature to a very high temperature, so this will be an endothermic process. So first, if you can imagine, we're starting at negative 55, so on this graph this would be negative 55 degrees Celsius. We need to heat our ice up to its melting point, which is 0 degrees Celsius. So we're going to use the quantity of heat required would be the mass of my ice times something called specific heat, which I'm going to give to you, times the temperature change. So I'm going to go from negative 55 up to 0 degrees Celsius. So my delta T would be 55 degrees. So we're going to start with our mass of 25 grams. Our specific heat is 2.06 joules per gram degrees Celsius, and our delta T is 55 degrees Celsius. So my units cancel out, grams and degrees Celsius, and I'll be left with joules for that first step. So I'm going to pull out my calculator, and you guys can work along with me. 25 times 2.06 times 55 degrees Celsius. Looks like I'm allowed, only 2 sig figs here, 2,800 joules for that first step, going from negative 55 to its melting point, which for ice, water, is 0 degrees Celsius. Now what I need to do is melt the ice, and so I'm going to use my heat of fusion. So you can see on my graph right here, I'm at point B, and I need to melt it and get it all into its liquid phase to C. So that takes energy for that phase change, and that's called heat of fusion. So I have my 25 grams, and it requires 334 joules per gram of water to melt. So let's see how much energy is required for that step. 25 times 334 joules per gram. I'm allowed 3 significant figures here, so 8,350 joules for this next step. 8,350. Okay, now I've successfully gotten to point C. I've melted my ice. Now I have all liquid water, and I need to heat that water up to its boiling point. So that's going to be a Q equals the mass of my liquid water times the specific heat of liquid water times my delta T. Now my delta T this time will be from its melting point to its boiling point. So it'll be 100 degrees Celsius. So I have my 25 grams. The specific heat of liquid water is different than solid water. It's 4.18 joules per gram raised 1 degree Celsius. And my delta T would be my 100 degrees Celsius. Once again, from its melting point to its boiling point. So degrees Celsius cancel, and so do grams again. So we have 25 times 4.18 times 100. It's like we have 3 sig figs again. It's 10,450, so we're going to say 10,500 joules to take it up to its boiling point. So right now we're on part D of my graph. And now we need to boil all of that water. So that's my heat of fusion, and get it turned into a vapor. So we need to vaporize or boil all that water, and the heat of vaporization of water is quite a bit higher than its heat of fusion, as you would suspect, because we have to separate those molecules from each other by huge distances. So we have the mass of our water, and the heat of vaporization is 2,260 joules for each gram of water that we want to vaporize. So let's see what that would be. 25 times 2,260. We're allowed 3 significant figures again, and that's 56,500 joules to vaporize all of my water. So on my graph, I'm right here. All of my water in its vapor state, and I need to take it to its final temperature, which is 225 degrees Celsius. So I need to take it to 225 from 100. So let's see, if we're going to go from 100 degrees Celsius to 225 degrees Celsius, that would be a 125 degree temperature change. So that's going to be the mass of my water times the specific heat of steam, which is different than liquid water or solid water, 2.02 joules per gram, raised 1 degree Celsius, and we have to raise that 125 degrees Celsius, its final temperature. So let's see how much energy is required for that step. 25 times 2.02 times 125, and it looks like we're allowed 3 significant figures again, so 6,310 joules. So we're going to have to add these together to find out the total heat that will be required for that change, once again, from of 25 grams of ice from negative 55 to positive 225. So it looks like my, when I add these up, I have to look at my least accurate value, and it looks like it's in the tens position here. So I'm going to round this off to the tens. So I have 2,800 plus 8,350 plus 10,500 plus 56,500 plus 6,310. And that gives me a total of 84,460 joules would be required for that change, which of course would be 84.46 kilojoules of energy would be required to take my 25 grams of ice from negative 55 to 225 Celsius. Okay? All right, that wraps up this chapter. That was a quick video for you today. We'll see you soon. Bye-bye. All right. Isopropyl alcohol. You guys probably have this at home. Yeah. It's 70% isopropyl alcohol. What's the other 30%?
Water.
Water. And I'm just going to pour it in the speaker and take a look at it and tell me whether it's a homogeneous or heterogeneous mixture. Sort of an easy question. Why homo? It's a solid.
I mean,
Okay. We are doing this for the honors class, but don't play dumb on purpose.
It's the same throughout.
It's the same throughout. We have what, one layer, right? One phase, and so it's homogeneous. And I have just a piece of an old cotton T-shirt. And isopropyl alcohol is flammable. So of course, with flammable things, what would you like to do? Burn them. And so we have a Bunsen burner here. You guys know how to use these. We'll get this ready. And we'll just wring a little bit of the isopropyl alcohol water mixture from the shirt. And we'll light it on fire. And then of course as it burns, just make to what I would think would be a pretty obvious observation.
table's on fire.
Besides the table. The table is burning. Okay. I guess I could do it over the floor, and then you'd say, well, the floor is on fire, so we'll just leave it here. Maybe it's not quite so obvious. Look.
It's not burning.
It's not burning.
It's not burning. Come stick your hand here in the flames and then tell me it's not burning.
I'll dip it in the alcohol first.
What's not burning?
Sure.
Yeah, the cotton cloth is not burning.
Oh, now it is.
The little part is.
I might get a little bit.
It is.
Yeah, it's burning. It's really burning.
Yeah,
I guess I didn't have enough water. There's a reason if I run out of moisture, we'll talk about why. Okay, if we to feel the cloth right now, besides being a little bit warm, it's almost completely dry, isn't it? I mean, it's pretty close to being completely dry. The reason that this part burned was because it did end up getting completely dried. And of course, the reason for that relates to that swimming pool story that we've told before in sort of a weird way. When you get out of a pool on a hot summer day, it might be 100 degrees outside, but when you get out of the pool, what do you start doing? Feel cold? You start shivering, your lips turn blue, you get goosebumps all over your body. But it's still 100 degrees outside. So why do you get so cold?
Because water evaporates.
You have a liquid evaporating, don't you? And evaporation is what type of process? It's a cooling process. So can we relate that to this rag? Was this rag moist with alcohol and water mixed together?
Yeah.
And so we got a lot of heat from the burning alcohol, but a lot of that heat, of course, it was released to the surroundings, but this moist rag was also part of the surroundings. So a lot of that heat energy went into doing what? Evaporating the liquid, either the isopropyl alcohol, which didn't take as much energy as the water. And I wonder if perhaps, so maybe having a 70% alcohol and water mixture, I wonder if I bumped it up to maybe a 60 or 50%, wouldn't I have more water in here that wouldn't be burning, which could absorb more of the heat and maybe cause it not to do that? Okay, so just keep in mind there's an exothermic process happening there when it burns, and then an endothermic process occurring as we evaporate that water and the alcohol. Okay? Not correct, Joe.